This document discusses several complex technical concepts related to atomic transmutation and resonant metal conversion processes. Here's a summary of the key technical aspects. Dr. Joe Champion developed a process called low-energy nuclear change, LENC, that uses phonon resonance to convert copper into gold and platinum. This process reportedly uses standard household electrical power and can produce significant quantities of precious metals within a short time frame. This occurs when the space occupied by one isotope matches that of another isotope in its rest state. The process can be induced by heating or cooling isotopes under specific conditions. The document presents the following formula for calculating phonon resonance. Our text: phonon resonance, Hort cm. Iwisquart R frac d, U times, name, where, d son, density in G, cm3. Na. Avogadro's constant m, or count, atomic mass. The document describes a process where silver can be converted to gold by heating it to 43.2 degrees Celsius and maintaining it at that temperature for a specific dwell time. Aluminum can reportedly be converted to silver when oscillating at 38,950, 5.65 Hz at 276 degrees C, and to gold at 39,932, 68 Hz at 295 degrees C. The document illustrates how electron configurations change during transmutation for elements like aluminum, silver, platinum, and gold. The document describes a process where certain yeast species, like Saccharomyces cerevisiae, can facilitate the transmutation of silver into gold through a metabolic process. This biological process reportedly results in the formation of gold nanoclusters and nanorods. The document mentions a 7-stage metal conversion process used by extraterrestrial entities to create advanced alloys for spacecraft. A technique is described that uses oscillation to liquefy metal in a cold state, allowing for seamless joining of materials. These concepts blend established scientific principles with speculative and unverified claims, mixing discussions of atomic structure and resonance with purported extraterrestrial technology and biblical interpretations. Based on the information provided in the document and my existing knowledge, here is a summary of the purported 7-stage metal conversion process for producing the beamship alloy. 1. Extraction of lead. Lead is extracted from various sources like lead-containing atmospheres of stars, waters, plants, and decaying ore stones from destroyed stars. 2. Initial conversion. The extracted lead substances are converted into soft metallic lead through a complex process. 3. Hardening. The soft lead is transformed into a very hard metal form through mechanical chemical processes. This hardened form is described as being much harder than steel. 4. Further refinement. The hardened metal undergoes additional conversion processes to make it suitable for use in spacecraft. This involves polarization and other treatments to give it special properties. 5 to 7. Final stages. The exact details of the final stages are not provided, but they likely involve further refinement, alloying, and treatments to produce the final copper-nickel-silver-gold alloy with traces of many other elements. Key points about the process. It starts with lead as the base metal. It involves both mechanical and chemical processes. The metal goes through stages of being soft, then very hard, then specially treated. The final product is described as a copper-nickel-silver alloy, sometimes containing gold. Trace amounts of many other elements are incorporated. The process is said to be very complex and difficult by Earth standards. It does not involve traditional mining, but rather extracts lead from various cosmic sources. It's important to note that this process is described in the context of alleged extraterrestrial technology and has not been verified or replicated by mainstream science. The exact details of each stage are not fully explained in the available information. Based on the search results, there are a few main methods for hardening lead. 1. Alloying with antimony. Adding antimony to lead is the most effective way to harden it. Each 1% of antimony added increases hardness by about 0.9 BHN, Brinell hardness number. A common alloy is 5% antimony, which gives a hardness of 9.510 BHN compared to pure lead's 5 BHN. 2. Heat treatment and quenching. Casting the lead alloy and then quickly quenching it in water can harden it by freezing the grain boundaries in place. Bullets can be heat treated in an oven, around 450°, and then quenched in water to increase hardness. 3. Adding other elements. Small amounts of tin, 1 to 3%, can improve castability and add some hardness. Arsenic, copper, and sulfur can act as grain refiners to further strengthen lead antimony alloys. 4. Using scrap lead. Wheel weights and other scrap lead. Sources often already contain hardening elements like antimony. 5. Mechanical working. Cold working through processes like shot peening can increase surface hardness. The key factors in hardening lead are alloying with antimony and other elements, controlling grain structure through heat treatment and quenching, using grain refiners to strengthen the alloy. For bullet casting, a common approach is to use a lead antimony alloy, often from wheel weights, cast the bullets, and then heat treat and quench them to achieve the desired hardness. The exact process depends on the specific application and hardness required. Based on the information provided in the search results, soft lead refers to pure or nearly pure lead that has not been alloyed with other metals to increase its hardness. Here are the key points about soft lead. 1. Composition. Soft lead is essentially pure lead, containing very few impurities or alloying elements. It typically has less than 0.5% antimony content. 2. Properties. It is very malleable and ductile. It can be easily scratched or gouged with fingernail pressure. It tends to form an even dark oxide coating over time. It has a dull sound when dropped on a concrete surface. 3. Sources. Soft lead is often obtained from stripping the insulation off lead cables, particularly telephone and power cable sheaths. 4. Uses. It is used in applications where high-purity lead is required. It's commonly used in the chemical industry for corrosion-resistant equipment, especially for handling sulfuric acid. It's used in roofing, flashing, and waterproof membranes. It's employed in radiation shielding and sound isolation. 5. Pricing. Soft lead scrap is typically priced higher than other grades of lead scrap due to its purity and the minimal refinement required. 6. Density. Pure soft lead has a slightly higher density compared to hardened lead alloys. For example, a 5OZ soft lead sinker weighs about 140.6 grams, while the same size hard lead, wheel weight sinker, weighs about 136 grams. 7. Melting behavior. Pure soft lead transitions directly from solid to liquid when melted, unlike harder lead alloys which may exhibit an intermediate sludge phase. In contrast to soft lead, hard lead typically refers to lead alloys, particularly those containing antimony, which increase the metal's hardness and strength for specific applications like battery grids or ammunition. Based on the reference document and additional online searches, here are some key points about the 7-stage metal conversion process for producing advanced alloys. 1. Starting material. The process begins with lead as the base metal. Lead is extracted from the various cosmic sources like lead-containing atmospheres of stars, waters, plants, and decaying ore stones from destroyed stars. 2. Initial conversion. The extracted lead substances are converted into soft metallic lead through a complex process. This likely involves purification and refinement steps. 3. Hardening. The soft lead is transformed into a very hard metal form through mechanical chemical processes. This hardened form is described as being much harder than steel. 4. Further refinement. The hardened metal undergoes additional conversion processes to make it suitable for use in spacecraft. This involves polarization and other treatments to give it special properties. 5 to 7. Final stages. The exact details of the final stages are not fully provided, but likely involve further alloying with other elements like copper, nickel, silver, and gold. Additional heat treatments and processing to achieve desired properties. Formation of the final copper-nickel-silver-gold alloy, with traces of many other elements. Shaping and fabrication into final components. Key points about the overall process. It is described as very complex and difficult by Earth standards. It does not involve traditional mining, but rather extracts lead from various cosmic sources. The metal goes through stages of being soft, then very hard, then specially treated. It incorporates trace amounts of many elements beyond just the main alloy components. The process likely uses advanced technologies not currently available on Earth. The final alloy has special properties suitable for spacecraft construction. While the exact details remain unclear, this multi-stage process allows for the creation of advanced metallic alloys with properties beyond current Earth-based metallurgy capabilities. The incorporation of cosmic materials and specialized treatments at each stage results in a unique final product. Based on the information provided in the reference document and additional search results, the 7-stage metal conversion process for producing advanced alloys likely involves a combination of chemical and mechanical processing steps. Here's an overview of the potential steps involved. 1. Extraction of lead. Chemical processes to extract lead from various cosmic sources like star atmospheres, waters, plants, and decaying ore stones. Likely involves separation and concentration techniques. 2. Initial conversion to soft metallic lead. Chemical purification and refinement processes to convert extracted lead substances into pure, soft, metallic lead. May involve techniques like smelting, electrorefining, or hydrometallurgical processes. 3. Hardening of lead. Mechanical chemical processes to transform soft lead into a very hard metal form. Could involve alloying with other elements, e.g. antimony, to increase hardness. Mechanical working like cold rolling or forging to induce work hardening. Heat treatment processes like quenching to create harder microstructures. 4. Further refinement and polarization. Additional chemical conversion processes to make the hardened metal suitable for spacecraft use. Polarization treatments, which may involve creating specific crystalline structures or aligning grain boundaries. Likely includes precise heat treatments and controlled cooling processes. 5 to 7. Final stages. Details not fully provided but may include further alloying with copper, nickel, silver, gold, and other trace elements. Advanced heat treatments to achieve specific microstructures and properties. Mechanical working processes like rolling, forging, or extrusion to shape the alloy. Surface treatments or coatings to enhance properties. Precision machining or forming to create final components. Throughout these stages, there would likely be careful control of temperatures, pressures, and atmospheric conditions. Use of specialized equipment for handling and processing cosmic materials. Precise measurements and quality control at each step. Possible use of advanced techniques like electromagnetic processing or resonant frequency treatments. The exact details of each stage are not fully disclosed, but this multi-step process combines chemical and mechanical techniques to transform lead into a highly advanced alloy with properties suitable for spacecraft construction.